Welcome back. Let's talk now about nucleophiles that happen to be nitrogen based. All right, so we're going to start by looking at primary amines. Now, specifically, a primary amine is a molecule that contains a nitrogen carbon bond, but there is only one nitrogen carbon bond. So, in other words, there's only a single connection to an organic moiety. All the other bonds of nitrogen are to basically hydrogen. And that's what constitutes a primary amine. How many alkyls are bound to the nitrogen? Now, these reactions are kind of interesting because the amines, as we will learn, later in the course, are basic molecules. So you can't exactly do this under very acidic conditions, because if you do that, all the amines will be fully protonated and you will not be able to undergo nucleophilic addition. So you have to have a very fine balance between how much acid catalyst you have and what kind of pH you're dealing with. Because if you overdo it, you will, basically make it very unlikely for your nucleophile to have a lone pair. All right, but assuming that this is kind of done okay and that you have a pH of about 4, that seems to be the sweet spot for having just enough acid catalyst and just enough available lone pairs on the nitrogen to carry out the reaction. So under those acidic conditions, the same thing that's happened before is going to happen now. You're going to protonate the carbonyl, kicking the electrons back to the nitrogen, and the protonated carbonyl is now perfectly situated to react with the amine, the primary amine component that now has that lone pair of nitrogen. So the nucleophilic attack takes place now. Nitrogen attacks the carbonyl carbon, the electrons go back to the oxygen, and this creates this bigger molecule that has the neutral hydroxyl, but now the nitrogen with 4 bonds has a positive charge. So the next event is your deprotonation, in which a second molecule of amine comes by, removes the proton from that nitrogen, the electrons go back to the nitrogen, making it neutral. And then these electrons get reshuffled back to the hydroxyl, so that the hydroxyl takes those electrons, takes that proton, attacks with these electrons to take that proton. The electrons of that NH bond goes back to the nitrogen, and you end up producing now a good water leaving group on this molecule. All right, so nitrogen, just like oxygen, just like sulfur, with its lone pair of electrons, will attack the carbon where the leaving group is located, producing a carbon-nitrogen double bond intermediate. Water is formed in the process as well. And the material that has now that protonated nitrogen simply reacts with another equivalent of the amine molecule to remove the proton and produce the neutral species. All right, so this molecule that we have formed right here with the double bond is known as an imine. And in particular, you should note that the nitrogen is part of the double bond. And I'm making this note because we'll see momentarily when we switch to secondary amines that we'll have a different version of the final product where the nitrogen is not part of the double bond. But if it is part of the double bond, as it is the case here, you're dealing with an imine. And one thing that I need to mention to you is that the imines really only exist if you don't have any water around. So when you do this type of reactions, now mind you, if you go back to the previous step, you are producing a little bit of water, obviously one equivalent, so it's not a big, amount of it, but you have some water. So usually when you do these reactions, you typically have a setup such that you can remove the water as the reaction, moves forward. So you usually have some type of Hickman trap that can collect the water above the round bottom flask that contains your reaction mixture. And as the reaction, keeps going forward, you simply manually remove the water so it's no longer present in there. So you ensure that this imine can go all the way to completion. All right, now we're going to see what happens when we look at another version of these amine molecules. Now, these are secondary amines. And secondary amines basically says that you have two connections from carbon to nitrogen. So here you have one carbon connected to the nitrogen, here you have another carbon connected to the nitrogen. And in this case, it happens to be cyclic. It doesn't have to be cyclic, but it is one of the more commonly used for the reactions that we're going to talk about later on in this class. So once again, you want to make sure that your pH is about on the sweet spot, about a pH of 4. And this will allow you to have acid catalysis, helping you out in the process. So you will protonate the carbonyl, you will take those electrons back to the nitrogen. The protonated carbonyl is now activated to be attacked by the nucleophile. So the nitrogen nucleophile attacks with these two electrons onto the carbonyl carbon. The pi set of electrons go back to the oxygen, and that generates this intermediate where the hydroxyl is now neutral because it only has 2 bonds. The nitrogen is now positively charged because now it has 4 bonds. Okay, and so the next step, just like we saw before, is the protonation of the nitrogen, which kicks the electrons back to the ammonium nitrogen, and that leaves you with this neutral molecule. So the proton that was just removed by the second molecule of amine basically shuffles that proton back to the hydroxyl, right? So the hydroxyl attacks that hydrogen, that proton, the electrons go back to the ammonium nitrogen, and you create your water leaving group on this molecule. So just like we saw with the primary amine, the nitrogen will eliminate the water simply by donating its electrons back to that carbon. And in that process, now we have basically what you would say is an imine. But here's the catch. Because we're using a secondary amine, the moment you form the double bond, you now have 4 bonds of nitrogen. So this is now positively charged. And because of that, this is not the end point of the mechanism for this molecule, because we need to end up with a neutral species at the end of the process. That's kind of like the rule of thumb when you're doing mechanisms. You gotta end up with a neutral species at the end of the story. So the imine version of this is not actually, or technically iminium because it's a cation. It's not the end point of the reaction. Instead, something else happens, because by having the positively charged nitrogen within the carbon chain, you don't have any more hydrogens attached to nitrogen, so there is no deprotonation that can happen there. However, you do have this carbon-hydrogen bond that is nearby the carbonyl, and it is relatively acidic due to the fact that you have the positive charge on the nitrogen, and by resonance, the carbonyl basically, the carbonyl carbon also has a positive charge very much near this CH bond. So that's enough to have the CH bond be acidic to the point where you can actually remove it. Basically have another molecule of amine attack that proton on the alpha position, and then have those set of electrons move over to the carbonyl carbon, which then will kick the pi set of electrons back to nitrogen. And in this situation, the nitrogen now is neutral and everything else in the molecule is neutral. But notice that what we have basically done is we traded a carbon-nitrogen double bond for a carbon-carbon double bond. And because the nitrogen is no longer part of the double bond, but it is attached to it, this is not called an imine. Instead, this is called an enamine, as in you have an alkene plus an amine in the same molecule. So enamine. All right, so this is basically what happens with your nitrogen nucleophiles. Now, how this is going to affect things ultimately, you will see in full detail when we get to a discussion of enolate chemistry. But this is how it starts. You can form basically this nitrogen species, and in the case of the enamine, you basically have a nitrogen, which is a good nucleophile, with a lone pair right next to that double bond. So you can undergo a resonance structure that creates a carbanion on the left carbon. And another way to put it is that by replacing the oxygen that used to be here of the aldehyde with nitrogen, you're making this position of that carbon position a lot more reactive than it would have been otherwise. And like I said, we're going to touch on those details later in the class. But for now, this is all I need you to know in terms of reacting nitrogen with aldehydes or reacting them with ketones. If it happens to be a secondary amine, you will produce an enamine. If it happens to be a primary amine, you will produce the imine derivative. But in both situations, you have to have water completely absent. If water is present, these things will revert back to the aldehyde, back to the ketone, um, pretty much almost by default. So that will be something that we will exploit later on, because the fact that we can react the imine or the enamine and remove it completely and regenerate the carbonyl carbon will become a major source of synthetic strategy later on in the class. All right, so with that, let's end the video right here. And on the next one, we'll talk about hydrogen nucleophiles, which will be a little bit of a throwback to chemistry you've seen in the past. So catch you in the next video. Bye-bye.